everyone, welcome back. Today we're going to deep dive into something kind of wild. We're going to see how throwing dice can actually help us understand radioactive decay.
Really?
You might be thinking, wait, what?
Yeah.
I know it seems strange, but trust me, it'll make sense. We're going to be looking at a cool web page from Open Educational Resources and Open Source Physics at Singapore. They have this JavaScript applet called Dice Throw.
Dice throw. Okay.
That's going to make everything crystal clear.
So it's amazing how a simple simulation like that can really bring these complex scientific ideas to life.
Absolutely. So imagine this. You have a bunch of dice, right?
Okay.
And each die is like a tiny radioactive nucleus.
Exactly.
Yeah.
And each time we roll the dice, it's like a unit of time passing. And here's the key. Let's say we decide that if a die lands on a 6, it decays, and we get rid of it.
So it's like a game where some dice disappear with each roll.
Exactly. And this disappearing act is actually a really clever way to visualize radioactive decay. You see, at the heart of every atom is this tiny nucleus, and it's packed with protons and neutrons. Now, in some atoms, this nucleus is unstable.
Unstable.
It's like it has a bit too much energy and wants to find a more relaxed state.
Okay, so it's like the nucleus is trying to chill out a bit.
Yeah, you could say that.
Yeah.
And the way it chills out is through radioactive decay.
Yeah.
It releases energy and particles to become more stable.
Got it. But I'm guessing it's not like every nucleus decides to decay at the exact same time, right?
You're absolutely right. And this is where probability comes in. Each radioactive nucleus has a specific probability of decaying within a certain time frame. It's similar to flipping a coin. You have a 50-50 chance of getting heads or tails.
Yeah.
But you can't know for sure what each individual flip will be.
So it's like a game of chance for each nucleus. We can't predict when one specific nucleus will decay, just like we can't predict a single coin flip.
Exactly. It's all about probability. Now, when we talk about a large group of atoms, we use the term half-life. Think of it this way. Imagine you have a bag of popcorn kernels, and every minute, half of them pop.
Okay, I can picture that.
That's kind of similar to how half-life works. It's the time it takes for half of the radioactive nuclei in a sample to decay. And going back to our dice simulation, if we set the probability of a die decaying to, let's say, 16, we can actually watch how the number of dice decreases over time, just like radioactive nuclei would.
So we're seeing this visual representation of how that decay happens over time, and this simple act of rolling dice provides a surprisingly accurate model for understanding a phenomenon that shapes our world in profound ways: radioactive decay. But why is understanding radioactive decay so important? What's the so what factor here?
That's a great question. Radioactive decay is fundamental, and it affects many areas of our lives. Take medicine, for example. Radioactive isotopes, which are atoms with those unstable nuclei, are used in tons of medical procedures. Like in PET scans, a tiny amount of a radioactive tracer is injected into the body. And this allows doctors to actually see how organs and tissues are functioning.
Wow, so it's like having a tiny radioactive flashlight to see inside the body. That's truly remarkable.
It is. And then there's archaeology.
Archaeology.
Scientists use radioactive decay, specifically carbon dating, to figure out the age of ancient artifacts. It's how we've been able to piece together the timeline of human history.
So radioactive decay isn't just about physics, it's a key to unlocking secrets of our past. This is already blowing my mind. Can we dig a little deeper into how carbon dating works? I'm curious about how something that seems random can help us be so precise about dates from thousands of years ago.
Of course, it's actually a really fascinating process. You see, all living things absorb a small amount of a radioactive isotope called carbon-14 from the atmosphere.
Okay.
So yes, even we are taking in a little bit of it right now.
Hold on, so we're all a little bit radioactive.
In a way, yes. But don't worry, it's a very tiny amount, and it's naturally occurring.
Okay, phew.
Anyway, when an organism dies, it stops absorbing carbon-14, and the carbon-14 that was already in its body starts to decay at a known rate.
Okay, I'm following so far.
So by measuring the remaining amount of carbon-14 in a sample, scientists can calculate how long ago that organism died. Think of it like a clock that starts ticking the moment something dies.
That's incredible. We're using a natural radioactive clock to look back in time.
Exactly. And because carbon-14 has a relatively long half-life, about 5,730 years, it's especially useful for dating artifacts that are thousands of years old. We've learned so much about human history through carbon dating.
Okay, so we've talked about the dice simulation, we've touched upon the randomness of decay, and we've even looked at how it helps us understand our history through carbon dating. What stands out to you the most so far?
I think what's truly mind-boggling is how this phenomenon which is governed by pure chance at the atomic level, can help us reconstruct history with such remarkable accuracy. This interplay of randomness and predictability is one of the most intriguing aspects of radioactive decay. But we've only scratched the surface. There's so much more to explore. It's fascinating to think about how this concept of radioactive decay, which we've been exploring, through Dyson probability, is actually connected to something as powerful as nuclear energy.
That's what always blows my mind about physics. It's like you start with something small and then realize it has these massive implications for like the whole universe.
You're absolutely right. And one of the biggest examples of that is how the energy released during radioactive decay, specifically through nuclear fission, is what powers nuclear power plants.
So we're basically harnessing the energy of these tiny, unstable nuclei to create electricity. That's incredible when you really think about it.
It really is. And of course, it brings up some important questions about how we use that power responsibly. Nuclear energy has enormous potential, but there are also real challenges when it comes to safety and making sure it's used ethically.
That's a great point. It seems like there are strong arguments on both sides. Some people see nuclear energy as this clean and efficient way to move away from fossil fuels. They say it could help us reduce carbon emissions and fight climate change.
And those arguments often focus on how nuclear reactor technology and safety measures have gotten so much better over the years. The goal is to minimize the risks of accidents and figure out the best ways to deal with radioactive waste.
But then there are also the concerns about what could happen if there is a nuclear accident. Plus, there's the issue of storing radioactive waste long term. And some people worry about the possibility of nuclear weapons technology spreading.
It's definitely a complex issue, and it's important to consider all those perspectives. We have to weigh the potential benefits of nuclear energy against the inherent risks and have honest conversations about how to move forward responsibly.
It's a reminder that science isn't just about discoveries and equations. It also has these big ethical and societal implications that we can't ignore.
Absolutely. Science is a part of human experience, and we have to think carefully about how we apply it and what choices we make.
You mentioned earlier that scientists use carbon dating to determine the age of ancient artifacts. Can you tell us a bit more about how that works?
Sure. Carbon dating is based on the fact that all living organisms constantly absorb a small amount of carbon-14 from the atmosphere. When an organism dies, it stops taking in carbon-14, and the carbon-14 that's already there begins to decay at a very specific rate.
So it's like a timer starts ticking the moment something dies.
Exactly. By measuring how much carbon-14 is left in a sample, scientists can calculate how long it's been since that organism died.
That's so cool, but I'm wondering if the amount of carbon-14 in the atmosphere has always been the same. What if it fluctuated throughout history? Wouldn't that affect the accuracy of carbon dating?
You're right to ask that atmospheric carbon-14 levels haven't always been constant. Things like volcanic eruptions and solar activity and even human actions can change how much carbon-14 is in the atmosphere.
So if the baseline carbon-14 levels have changed over time, wouldn't that mess up the calculations for carbon dating?
That's where the ingenuity of scientists comes in. They've created ways to calibrate carbon dating by using data from tree rings, ice cores, and other sources that record past carbon-14 levels.
So they're basically fine-tuning the carbon dating clock by looking at historical records.
Exactly. By comparing the carbon-14 levels in a sample to these calibrated records, scientists can adjust their calculations and get more accurate estimates of how old something is.
It's like a puzzle where they're using all these clues to get the most accurate picture of the past.
It really is. And that brings up another interesting point. We've been talking about how radioactive decay is a random process. But if it's random, how can scientists be so precise with their calculations, like figuring out the exact age of an artifact or the half-life of an isotope?
That's a great question. It seems counterintuitive that something random could lead to such precise measurements.
It is a bit of a paradox.
Yeah.
But think about flipping a coin. If you only flip it a few times, you might get a bunch of heads in a row or a bunch of tails. The results seem unpredictable.
Yeah, it's like sometimes you get lucky and win a few coin tosses in a row.
Exactly. But if you flip a coin thousands of times, you'll start to see that the results even out. Roughly half the flips will be heads and half will be tails. The more times you flip, the closer you get to that 50-50 split.
So it's the law of large numbers in action.
Precisely. And the same thing applies to radioactive decay. Even though individual nuclei decay randomly when you're looking at a large sample, the overall pattern becomes predictable, and we can describe that mathematically.
It's amazing how randomness at the microscopic level can lead to this kind of predictability on a larger scale.
It's a perfect example of how nature often works in seemingly contradictory ways. There's both this element of chance and this underlying order.
It's like the universe is playing dice, but it's playing by certain rules.
That's a great way to put it. And because of that, we can use the principles of radioactive decay to do incredible things like determine the age of ancient artifacts with remarkable accuracy.
This deep dive has been so insightful. It's amazing how a simple simulation like dice throw can open up all these fascinating ideas about the universe.
It really highlights how important it is to find creative ways to make science accessible and engaging for everyone.
Absolutely. It's all about sparking curiosity and empowering people to explore the wonders of science. It's like we've gone on this incredible journey, from the randomness of throwing dice to the profound implications of radioactive decay.
We've seen how it affects fields like medicine archaeology and energy production.
Hmm.
And we've talked about probability statistical patterns and the ongoing pursuit of scientific accuracy.
It's been a truly fascinating exploration, but before we wrap things up, I have one final thought-provoking question for you.
I'm ready. Bring it on.
Okay, here it is. We've talked about how carbon dating helps us understand the past, but how do scientists use radioactive decay to understand the future?
That's a great question. And it's one that takes us into some truly mind-blowing territory. When we talk about using radioactive decay to understand the future, it's important to remember that we're not talking about predicting specific events like in a fortune teller's crystal ball.
Right, it's not like we can use radioactive decay to see what lottery numbers we'll win next week.
Exactly. Instead, we're talking about understanding long-term processes and potential outcomes based on what we know about how radioactive materials behave.
Okay, that makes sense. So what are some examples of how we use radioactive decay to look ahead?
One really important example is in managing nuclear waste. As you know, the waste produced from nuclear power plants remains radioactive for a very, very long time.
Yeah, that's one of the big concerns about nuclear energy.
It is. And scientists use their knowledge of radioactive decay to figure out how to safely store that waste so it doesn't pose a risk to people or the environment.
So they're basically using radioactive decay as a guide to make sure the waste is contained for as long as it takes to become safe.
Precisely. They have to consider things like the half-lives of the different radioactive isotopes in the waste and how long it'll take for the radioactivity to decay to a safe level.
That sounds incredibly complex.
It is. It's a huge scientific and engineering challenge, but it's essential for using nuclear energy responsibly. Another way we use radioactive decay to understand the future is in studying climate change.
Oh, interesting. I wouldn't have thought of that connection.
You see, scientists can analyze radioactive isotopes in things like ice cores and sediment layers to learn about past climate conditions.
So it's kind of like carbon dating, but for climate instead of artifacts.
Exactly. By understanding how the climate has changed over long periods, they can make better predictions about future climate trends and how we might need to adapt.
That's a really powerful tool to have in our fight against climate change.
It is. And it highlights how crucial radioactive decay is, not just for understanding the past, but also for shaping our future.
This has been such a fascinating deep dive. We've covered so much ground, from throwing dice to carbon dating to nuclear energy to climate change.
It's amazing how one concept can connect so many different areas of science and our lives.
It really shows how interconnected everything is. And I think we've given our listeners a lot to think about.
I hope so. If there's one thing I hope people take away from this, it's that science is not just about memorizing facts. It's about exploring the wonders of the universe and asking questions.
Absolutely. And it's about understanding that even something as seemingly random as radioactive decay can help us make sense of the past, present, and future.
Well said. So to all our listeners out there, keep asking questions, keep exploring, and never stop being curious about the world around you.
And that's a wrap on this deep dive. Thanks for joining us on this incredible journey into the world of radioactive decay.